Welcome to Earth and Sky Camp. The hands-on learning activities that I'm going to show you can increase anyone's understanding of the world. You'll be surprised at how accurately you can sketch maps using the drawing by squares method. You'll start by drawing the world on your computer and then on physical surfaces, like chalkboards and basketballs. We all have mental maps of the world. If you gave college students large sheets of paper and asked them to each draw and label a map of the world from memory, this is what you could expect to see. However, many students have mental world maps that are much less accurate. All Earth and Sky Camp activities are designed to enhance your mental map of the world. Drawing and labeling maps is the core activity, but you can also explore places using the map's links to photos, websites, and videos. The Earth and Sky quizzes will sharpen your locational knowledge of cities and stars. The format of the map makes it easy to remember these locations because it can act as a memory device. All of the app's maps are based on the manual map projection. Map projections are geometric systems for converting a three-dimensional spherical surface into a two-dimensional flat surface. Associating the 24 primary squares of the map with the 24 segments on your fingers is the key to remembering locations. The manual map projection is a type of mnemonic device. Mnemonic is a Greek word that means memory. There are different types of mnemonic devices. The most common are name mnemonics. These are acronyms and phrases, like the word Holmes. Each letter refers to one of the Great Lakes: Huron, Ontario, Michigan, Erie, and Superior. Most children use the ABC song to learn the alphabet. That's music mnemonics. Before the invention of printing, image mnemonics was the most common device. It was used for lists of things like people and places. It can also be called spatial mnemonics. This device was invented by the Greeks and adopted by the Romans. A Greek speaker on a stage might be required to introduce important people at a theater. Before the event, he associates the names of these VIPs with where they will be seated. Days later, he finds that he can quickly memorize other people's names by mentally assigning them seats in that theater. It was also common to associate lists with the seating of rooms in a palace. Europeans who spoke Latin were still using the method of loci in the Middle Ages. Your 24 finger segments are similar to the seating sections of a theater or the rooms of a palace. By dividing them into blue and red zones, you organize them symmetrically. The blue and red color zones are 30 degrees wide. There are 6 zones of each color. Each finger segment represents 60 degrees and has both a blue and red zone. In this illustration, the finger segments are not aligned, but if you cup or curl your fingers, you will see that the segments do line up to form a grid. They will also appear more square. The app displays 17 views of an Earth map and 1 view of a sky map. The partial views of the Earth are based on the 4 directions of north, east, south, and west. The Earth maps are shown at 3 different scales. The world map is the default view. Dividing it along the equator and the prime meridian results in the northwest, northeast, southwest, and southeast views. These 4 views are displayed separately at twice the scale of the world map. The northwest view is the top left portion of the world map. This view can be similarly divided into 4 sections. The northeast-northwest map is the top right quarter of the northwest map. It's one of the 12 views that is displayed at 4 times the scale of the world map. The default view of the app is the study mode. The buttons display the locations of cities, waterways, areas, and videos. The clear button removes all information displayed over the map. Clicking on the Waterways button will display the names of navigable bodies of water, like oceans and seas, as well as large lakes and rivers. Depending on the scale of a map, clicking the Areas button will display the names of continents, nations, and islands. Clicking on the Cities button will display circular icons where major cities are located. Mousing over these icons will display a photo and the name of the city next to the map. Clicking on a city's icon will open a new browser tab with a search for the city. Clicking the Videos button will display icons of the map that link to YouTube videos. Pointing at an icon with your mouse will display a small embedded video next to the map and its title below the map. You can click on the embedded video to watch it, but clicking on its circular icon will open a new tab where you can watch a larger version of the video on the YouTube website. The quiz mode provides an activity to strengthen your locational knowledge of cities and areas. There are quizzes for every map. If you can correctly click on a city or area's location, a check mark appears after the name. The location's distance from an incorrect click is indicated by numbers with horizontal and vertical arrows. There is a saying that the map is not the territory. The scientific models we make to understand reality are never the same as the reality. When you compare a globe to the manual map, you can see that the straight black lines on the map are actually circles on a globe, and the top and bottom horizontal lines of the map are actually points on a globe. The north and south poles are represented on the map with a line that's the same width as the equator. We can use the map's straight black lines with the drawing by squares method. The Egyptians were using this same method almost 4,000 years ago to make large drawings and sculptures. After a grid of squares has been placed over an image, it can be transferred to a grid of larger squares by copying it one square at a time. As long as each square is roughly the same, the enlarged drawing will be very similar to the original image. The app's primary sketch tools are a pen and eraser. Both work by clicking and dragging your mouse. There is also an undo and a clear button. Clicking clear removes everything you have sketched, and clicking undo removes whatever you added last. There are also shortcut keys to enable you to more quickly correct your sketch map without moving the mouse back and forth to the control panel. Press the U key for undo, and pressing either the E or P characters on your keyboard will toggle between the pen and eraser tools. Clicking the text button will turn off the shortcut keys for the undo function and the pen and eraser tools. With the text tool selected, whatever you type will be saved. It can then be positioned as a label wherever you next click the mouse. Because you can't see the text before you position it, you will often need to click the undo button and retype the label to best position it. The dot tool is used for indicating cities and stars. The line tool is used for drawing constellations, and arrows for the labels. Lines are drawn by clicking the mouse in two spots. You often need to change the colors of dots and lines with the black, blue, and red buttons. The number below the color buttons indicates the sizes of dots, lines, and text letters. You can increase or decrease the number to change their size. The Pen and West buttons are selected by default when you start to sketch an earth map. You will need to click the East and the Grid buttons to the right of the West button in order to sketch both the west and east sides of a map. For example, this is the view you will see when you start to sketch the Northeast-Northwest map. The coastlines and islands are shifted to the right side of the map so that you can copy them onto the western squares. Whenever you sketch a map, the best approach is usually from west to east and from north to south. You should draw continents before islands and large islands before small ones. Note that drawing accurately with a computer mouse is more difficult than with a marker or with chalk. Zooming your browser in to make maps larger can help. Click the East button to copy the eastern squares of a map. This will display the eastern areas on the left side of the map. When you click the Grid button, you will see the app saved whatever you sketched on the western side of the map. That Grid button will now display the word All. Clicking the All button will display the full map below your sketch map. This view enables you to check how accurately you have copied the squares. Use the Eraser tool to remove inaccurate lines. Some areas are more difficult to draw than others. The islands of Great Britain and Ireland are especially difficult because they are very small and have irregular shapes. Click the West and East buttons to correct the erased lines. You might be tempted to just trace the lines from the All view of the map below your sketch. However, this will not help you to properly observe the locations and shapes of coastlines and borders. Notice that some of the crosshairs are darker and heavier than others. They indicate important locations for drawing coastlines more accurately. For example, Ireland is only 5 degrees wide. Its eastern coast begins at 6 degrees west and its west coast ends at 11 degrees west. The dark crosshairs above and to the left of Ireland can help you locate it more precisely. There are 3 types of crosshairs on the maps. Center crosshairs are surrounded by small circles. The corner crosshairs indicate the 15-degree wide squares. The smaller crosshairs occur at 5-degree intervals. Noticing where these darker crosshairs occur in relation to coastlines is the key to being able to accurately sketch a world map. After you complete the coastlines, use the dot tool to locate important cities. You may need to open another tab on your web browser to view the location of cities in the app's study mode. Using blue and red dots will help you to associate them with a primary square's blue and red zones. You should include national capitals and large economic centers, but you can also locate any places that are of interest to you. The text tool is all you will need to label most places, but sometimes you will also need to use the line tool as an arrow to point to a dot. To draw a straight line with the line tool, first click on the city and then somewhere next to its name. After you have sketched a map, you can download it to your computer or upload it to the Earth and Sky Camp gallery. In order for your sketch map to be approved, it must be reasonably accurate, and you need to enter your name, age, school, and city. It can take several seconds for your map to upload after clicking the Submit button, so wait before clicking anything else. If the upload is successful, the app will display the message, Sketch Map Uploaded. In the future, you will need to log in order to upload maps or photos to the gallery. This will make it easier for you and the people who know you to view your maps. After being approved, sketch maps are currently displayed according to their scale and upload date. The most recent and smaller scale maps are displayed first. Below the computer maps, the gallery displays photos of maps and globes. The form for submitting photos is at the bottom of the gallery page. You can use the Drawing by Squares method to sketch maps on a variety of surfaces. These include chalkboards and paper, walls and floors, and basketballs. Remember that drawing a larger version of the map is easier than a smaller version. Sketching maps on your computer requires a mouse, as do the app's study and quiz modes. So they are not suited for mobile phones. However, students can use the manual maps displayed on their phones to physically copy them onto any physical surface. Drawing a world map from memory takes practice, and chalkboards are the ideal place to do it. You can use a yardstick to make a grid on the chalkboard, but it's faster to sketch one freehand. You can use your sense of symmetry to draw squares and to locate their centers. If a square looks too narrow or too wide, just erase and redraw one of its sides. In this grid, you can see the squares aren't perfectly square, but they're close enough for making a sketch map. Note that you should usually omit the row of squares south of 50 degrees. Including Antarctica will reduce the space you have for the rest of the world on your chalkboard. In this photo, you see a completed chalkboard sketch map. What you can't see without looking closely is that small dots have been drawn where the important crosshairs occur. Your natural sense of symmetry will enable you to divide squares in half and approximate the locations of the crosshairs. While quarter and 5-degree crosshairs are important for sketching coastlines accurately, the key to memorizing the map is to remember what is located at the center crosshairs. On your left index finger, centers occur at Alaska, Canada, and in the Arctic Ocean just off the shore of Greenland. On your right index finger, all center crosshairs are within Russia. The centers on your middle fingers occur in the Pacific Ocean, the city of New Orleans, the Atlantic Ocean, the cities of Cairo, Egypt, and Lhasa, Tibet, and in the Pacific Ocean. The centers of your ring fingers are in the Pacific and Atlantic Ocean, near the coast of South Africa, in the Indian Ocean, and near the eastern coast of Australia. The centers on your left little finger are all in the Southern Ocean, with the coastline of western Antarctica next to the corner crosshairs below them, whereas the coastline of eastern Antarctica runs along the center crosshairs on your other little finger. Students don't need to memorize the manual map in order to use it to study geography. Making maps in teams is an activity students can do together while seated at their desks. 4 to 8 students can be grouped into teams and given photocopies of 6x6 grids of squares. If each square represents 15 degrees of longitude, one sheet represents 90 degrees. You can download a printable PDF of this grid from the gallery page. Students must cooperate with each other in order to combine their drawings into a world map. Teachers will have to offer more help and supervision to some teams than to others. The manual map can also be expanded with sheets of butcher block paper. The best place to do this is in a cafeteria where students can work around large tables. Yardsticks are needed for making grids on the 36-inch wide bands of butcher block paper. The grid is drawn in pencil, and so is the map. However, markers are then used to draw the map's coastlines and borders. This activity will take more than one class period. Once you start looking, you will see lots of grids of squares already made. The overlapping cinder blocks and many school walls form square grids. But mostly, you will see grids under your feet. A tile floor or a stone courtyard at your school might be a good place for your class to sketch a map. This courtyard world map was sketched by several classes of students using sidewalk chalk. I located and labeled the latitude and longitude of the primary squares of the seams of the stone courtyard for the students. Prior to going outside, each class was shown on the chalkboard what squares they would be sketching. Copying the manual map onto a basketball is the ultimate manual mapping activity. It gives students the best reference for further development of their mental maps, and it also reveals a lot about the geometry of maps. The type of markers used in making a globe can vary, but some materials are always necessary. These are a basketball, cardstock guides, a crayon, a sharpener, pencil erasers, rubbing alcohol, and paper towel. This is a kit for making a Sharpie globe. And this is a kit for making a globe with acrylic paint markers. Different colors and brands of acrylic markers and paint can be used. The simplest way to make a basketball globe is with Sharpie markers and a gel pen. One Sharpie must have a fine tip and the other a chisel tip. You start making a basketball globe by using a crayon to draw a grid of 15-degree wide squares. I'll show you later how to use the cardstock guides to make the meridians and parallels. Once you've drawn the grid, you'll use a fine tip marker to draw the coastlines of continents and islands. Notice that some lines have been thickened and some islands filled using the fine tip marker. This is because the chisel tip marker is less precise and shouldn't be used in tight spots. Also, notice that you can add 5-degree crosshairs to your grid wherever you need them. Do this with the Sharpie marker inside continents and with the crayon in the ocean areas. Now you can use your chisel tip marker to complete the land areas. I don't recommend trying to draw national borders on your basketball. You should locate cities on your globe. They can provide indicators for the locations of countries. You should only mark cities you can locate correctly in quizzes. You can always add new white dots to your globe in the future. However, the cities on your globe should accurately reflect your mental world map. The globe can then continuously reinforce your study of the world. Your globe will look even better after you erase the grid. It takes some effort to remove the crayon marks with a pencil eraser, but it won't remove the Sharpie ink if you've given it time to dry. Now let's look at how you actually draw the grid on a basketball. Remember, the manual map has 24 primary squares. They are each 60 degrees wide. The black stripes on your basketball are spaced 45 degrees apart. But because the manual map grid is based on 15-degree wide squares, we can regroup the squares to match the stripes. These stripes will correspond to meridians on your globe. All meridians are 1/2 of a circle. These circles divide the Earth into 2 even parts. The equator is also a circle that divides the Earth in half. Its location is based on the spinning movement of the Earth. The equator is a parallel, and all parallels are aligned with the spinning movement that causes our daily 24-hour cycle. Meridians are all the same size and intersect each other at the north and south poles. Parallels keep the same distance from other parallels and become smaller as they approach the poles. There are 2 common sizes of basketballs. Size 6 is used in women's basketball and for middle school students. Size 7 is the regulation size used in the NBA. The 2 cardstock guides in each kit have links that are half the circumference of the ball. The bottom edge of the rectangular guide is used to mark the locations of parallels on the stripes. The top edge is used for drawing the equator and marking where meridians cross it. The edges of the curve guide are used for drawing meridians and marking where parallels cross them. The air valve on a ball indicates where the equator crosses one of the black stripes. Align the 0-degree mark on the rectangular guide with the hole in the valve. Then check that the 90-degree marks align with the stripe intersections on the top and bottom of the balls. Note that the 75-degree mark should align with the intersections of the curved stripes and their adjacent straight stripes. First, use the rectangular guide to mark the locations of parallels on the stripes. You can only mark half of the parallels along a stripe before you will need to move your hand to hold the other half of the guide down along the stripe. After you have marked the locations of parallels on all of the stripes, you will line the guide with the 0-degree marks. Use the edge of the guide to draw the equator. Only draw one 45-degree section at a time. You want to use the minimum amount of pressure to draw lines. Too little pressure results in gaps, but too much results in mistakes, thick lines, and broken crayons. Note that keeping your crayon sharpened results in the best lines. But crayons will easily break if they are too sharp. After you've drawn the equator, use the guide to mark off meridian locations every 15 degrees. You will use the edge of the curved guide to draw the meridians. Note that these guides should point to the stripe intersections on the top and bottom of the ball. Also note, you should always draw meridians with your hands positioned in the same way. For example, if you are right-handed, you will keep the guide positioned in the center with your left hand and will use the edge on the right to guide your crayon. You can then turn the ball upside down to position your crayon on the other edge. After you've drawn all of these secondary meridians, you will use the curved guides to mark the locations of parallels. You will then be ready to sketch the parallels. When you view the parallels from the top or bottom of the ball, it's more obvious that they are circles. I recommend that you sketch the 75th parallels first, because they are the smallest circles and they overlap the intersections of the curved and straight stripes. Then sketch the 60th and 30th parallels. Other than the equator, the shortest distance between the marks on the stripes is not along a parallel. The shortest distance veers away from parallels the closer they get to the poles. That is why airplanes do not fly due east or due west when flying to cities of similar latitudes. Once you've made the primary parallels appear circular, it's easier to sketch the others. For example, you just need to keep the 15th parallel equidistant between the 30th and the equator. Similarly, the parallel at 67.5 degrees is halfway between the 75th and 60th parallels. Use the 60th parallels to keep your 50th parallels circular, and the 40th will be halfway between the 50th and the 30th. The cartographic term for intersections of meridians and parallels is a quadrangle. The word just means four angles. Quadrangles are not squares or rectangles because they are formed by three-dimensional arcs of circles. You should see on your grid that the quadrangle between the equator and 15 degrees north and the quadrangle between 60 degrees north and 67.5 degrees north are both shaped like squares. However, the circumference of the 60th parallel is half that of the equator. That is why the darkened quadrangle at 60 degrees appears to have 1/4 the area of the one at the equator. Both quadrangles are 15 degrees wide, but the smaller one contains only 7.5 degrees of latitude, half that of the one at the equator. The lengths of degrees of latitude do not change, but the lengths of degrees of longitude decrease as they get closer to the poles. Despite the decreasing size of the grid's quadrangles until the 75th parallel, they are all roughly square. These quadrangles can all be sketched using the drawing by squares method. Be sure to click the Globe Grid button in the study mode to copy the squares onto your basketball. This will display what the longitude of the stripes should be. Most basketballs have logos printed on them, which you want to position next to the 180th meridian. You can match the stripes on the map by using either end of the ball as the North Pole, but only one end will result in the logo appearing below Hawaii. This also results in the least concealment of the Arctic coastline by the curved stripes. You will want to copy most of the squares from the largest scale maps. They will give you the best views of individual squares, and they will roughly show you what areas are concealed by the stripes. Beyond the 75th parallels, the coastlines of the map are extremely distorted and not useful for copying onto a basketball. It's much easier to copy these polar areas from maps. The gallery page contains polar maps that show the parallels at 60, 67.5, and 75 degrees. The parallel at 67.5 degrees is not standard. However, it's just 1 degree away from the Arctic and Antarctic circles at 66.5 degrees north and south. Antarctica is simpler to draw, but it's easy to misalign the meridians and rotate the coastlines 90 or 180 degrees. The prime meridian is at 12 o'clock here. Note that the ice shelves, which are colored white, can be ignored and not included with the coastlines. These are refillable acrylic paint markers, which you can use with any color of paint you want. The fine tip is similar to the Sharpie. The chisel tip is slightly smaller than the Sharpie I used on the previous globe. Then there is a wide-tipped marker on the right. The surface of a basketball is not ideal for marking with any type of marker because of the bumps. These bumps are called pebbles. Looking closely, we can see that a marker tip might not always contact the lower areas between the pebbles. This is one issue. The other issue is drawing precise lines on this surface. For example, if you were to try to draw an island with a wide or chisel tip marker, most of the paint would be placed on the tops of the pebbles. After 5 or 10 seconds, some of that paint might flow down into the lower areas. This can even happen with ink from a wide tip Sharpie. The key is to first use a fine tip marker, which makes more precise lines and releases less paint. As you continue to draw more coastlines, this paint will dry and form a barrier that wet paint or ink won't cross. You can then increase the width of the line with a chisel tip marker. However, in tight spots, you can avoid mistakes by increasing the width with more strokes from the fine tip marker. Also notice the black stripe on the left. You can see that it is painted on the ball because a streak of the orange rubber is showing from below. This is how the balls I used were made. More expensive balls use black rubber for the stripes. Also, notice the orange ridge next to the stripe. You sometimes need to use both fine and chisel tip markers to cover ridges and indentations. Don't use a wide tip marker this close to the stripes. There are several popular brands of acrylic paint markers such as Montana, Liquitex, and Decocolor. Montana makes the refillable markers with interchangeable tips. Any high-flow acrylic paint will work with them. The viscosity of the paint in all markers is lower than the acrylic paint that you would apply with a brush, and that is why there is that issue with it running between the pebbles. All paint markers work the same way. You push the tip into the barrel to get the paint to start flowing. A spring pushes the tip back out, and this pumping motion must be repeated 6 or more times to start the paint flowing. Note that the flow of the marker can slow, and you occasionally need to pump it to maintain the desired flow. Also, when you stop painting for a while, you should put the top back on the marker, and before you start painting again, you should test the flow with a piece of paper. Know how much paint will be flowing onto the ball before making marks. There is also a steel ball in every marker. When you shake the marker, the ball keeps the paint ingredients properly mixed. You should also be aware of the relative size of the pebbles to the land you are drawing. The diameter of pebbles is more than 2 millimeters, which corresponds to about 70 miles on the Earth's surface. Most cities are less than 10 miles wide. Fine tip markers make lines slightly smaller than a millimeter. Their width corresponds to about 23 miles. The smallest line you can make with a chisel tip is 2 millimeters, and that's close to 65 miles on your globe. This means it's impossible to show fine details on your globe. It also means you have to exaggerate the size of cities so that they will stand out. This is an example of coastlines and lakes drawn with a fine tip Montana marker. Note that the marker represents the water along the coastline and not the actual coast. Also notice the crosshairs in the ocean areas. You will want to place your ball in something like a coffee cup to keep it still while you are painting it. Realize that you will place whichever hand you don't hold the marker with on the ball to turn it as you are painting. If you are right-handed and touching the ball with your left hand, you will want to continue painting on sections to the left of what you've just painted to avoid touching the wet paint. Use a chisel tip to fill in all of the areas that are too small for the wide tip. These include the edges of the black stripes. Painting the lower surface between the pebbles is much faster and easier with the wide tip marker. However, the larger volume of paint can easily flow onto stripes. Minimize mistakes by using the right tip in the right place, and you will finish more quickly. The cities were made on this globe using the same type of fine tip marker as I used on the coastlines, but with white paint. Note the cities on the black stripe. The stripe is roughly 200 miles wide. You want to balance keeping cities close to their actual size with making them large enough to see from a distance. It's easy to make them too large because the amount of paint that flows out the tip can vary. Most mistakes can be quickly removed with a piece of paper towel. Dipping the towel in water will remove larger mistakes. After the white paint has dried, you can erase the crayon grid with a pencil eraser. The light blue areas show where the chisel tip marker should be used. If you can't name a city, wait until you can before you add it to your globe. Cities not only provide references to their countries, we can reference lakes, deserts, and other physical features using the closest major city. 2/3 of the Earth are covered by oceans. Painting the oceans makes for a more traditional globe, but it's more difficult to draw islands. This is a size 6 and size 7 basketball. They were both painted with cerulean blue, but using different brands of paint, Golden and Liquitex. Compare the detail of the Caribbean islands with the same islands on the Sharpie globe. On the other hand, lakes are more difficult to draw when the original orange surface is used to represent water. However, drawing this type of globe is faster and less work. Being able to identify the cities on both types of globes is the key to their usefulness. There are a variety of colors that can be used, but high contrast is necessary between the ocean and the land with the cities. Note that the coastlines on this ball were drawn with a green chisel tip Sharpie. Its ink appears bright green on paper, but it turns very dark on the orange rubber surface. However, it may be a better choice than a black Sharpie because white cities will still stand out and there's more contrast between the dark green and the black stripes. Ink from blue Sharpies will also appear very dark. You will likely make a few mistakes whatever type of marker you use. Nobody will notice some of them, but you should know how you can correct them. Crayon grid lines can be removed with a pencil eraser. You may at first see some discoloration in the orange surface after you have removed them, but this is just eraser residue that can be easily removed with an old toothbrush and water. The stiffer and larger the brush is, the better. Wet paint can also be easily wiped off with paper towel, but it can dry fairly quickly. The best way to remove paint or ink is with rubbing alcohol. It works with both ink and pencil erasers. The pencil erasers that slide onto the end of a pencil or pen enable you to efficiently erase small mistakes. Pour some alcohol into the bottle's cap and dip the eraser into the cap. This greatly increases an eraser's ability to remove both ink and paint. When you erase with rubbing alcohol, you are diluting the paint into a liquid that sits on the surface. That's why you then need to use paper towel to wipe the ball's surface. After the paint is removed, you will then need to wash the residue off with water and a brush. The concept of scale is important in making maps and globes. This size 6 globe was made with a Sharpie, and the size 7 was made with black acrylic paint. We say basketballs have different sizes, but we say globes have different scales. When we use units to give the scale, such as 1 inch equals 873 miles on a size 6 ball, that's called a verbal scale. You will also see fractional scales printed on globes and maps. For example, the ratio of 1 to 55,721,600 means that whatever number of units of distance that you measure on your globe or map is 55,721,600 times larger on the actual Earth. This is called a fractional scale. It is easily converted into a verbal scale using metric units. 1 centimeter equals 557 kilometers. The concept of scale on map projections is more complex. The spherical three-dimensional surface of the Earth is projected onto a geometric shape that can be flattened to form a two-dimensional map. There are a variety of geometric shapes and many ways of positioning them to make different types of maps. The Mercator projection was designed in 1569 in response to the explorations of Western Europeans. Its map grid is based on where parallels would be located if a cylinder was wrapped around a globe and contacted the surface at the equator. An imaginary straight line from the center of the Earth determines where a parallel on the globe's surface will be placed on the cylinder. The cylinder is then unrolled to make the flat two-dimensional map. Note that a line passing through the poles will never contact the cylinder, and parallels above 85 degrees will be spaced at distances too large to be included on the map. On this Mercator map, meridians and parallels are spaced 10 degrees apart. At the equator, quadrangles are square, but at 60 degrees north and south, they are twice as high as they are wide. This corresponds to the proportions of quadrangles at 60 degrees. Because the 60th parallels have a circumference which is half the distance of the equator. The circumference of any parallel is equal to the cosine of its latitude multiplied by the circumference of the equator. This is why cylindrical projections have variable map scales. Note that a fractional scale is also usually given, and it refers to whichever parallel of a globe was in contact with the cylinder. This is usually, but not always, the equator. Bar scales are used for large-scale city maps. A graphic bar can be used anywhere on a city map, but you have to take note of the latitude of a parallel before you can use a variable scale to calculate distance on a cylindrical projection. The success of the Mercator projection was based on the fact that although it distorted the relative size of areas, it preserved the direction between them. With a compass and a sextant, Mercator projections could be used to navigate the oceans. Over 1,000 years earlier, Ptolemy had made a map of Europe, North Africa, and Western Asia. Mercator incorporated this information into his map. The Mercator projection then provided a tool for documenting maritime discoveries and completing the knowledge of the Earth's surface. Before Ptolemy lived, people understood that the position of stars and the sun in the sky were related to the latitude of their own location on a spherical Earth. They noticed that the altitude of the North Star was related to how far north they were. When they eventually sailed south of the equator, the North Star dropped below the horizon. However, explorers could only estimate the longitude of locations until the invention of the chronometer in the 1760s. The word chronometer was the original term for what we now call a pocket watch. It enabled explorers to finish accurately mapping the world. For example, when the sun was at high noon on the island of Fiji, the chronometer revealed that it was midnight in London. That meant London was 180 degrees away on the opposite side of the planet. The world rotates 15 degrees every hour. 24 times 15 equals the 360 degrees of the whole Earth. Actual time zones are often based more on political relationships than on longitude. For example, China is more than 60 degrees wide, but it only has one time zone. However, when the sun rises in Shanghai, it's still dark in West China. This is what a modern Mercator projection looks like. The North Pole can't be seen, but Greenland is almost as large as Africa. Its shape, however, is actually quite accurate. This animated GIF shows the size distortion on Mercator projections. The scale of the map gradually increases as latitude increases. Geography textbooks often recommend the Robinson projection over the Mercator because it more accurately shows the relative sizes of areas like Greenland and Africa. There is still some size distortion, but it's much less than the Mercator's. Note that the North Pole is represented by a horizontal line that is more than half the length of its equator. A sinusoidal projection does accurately reflect the relative sizes of areas. The lengths of parallels correspond to their cosines, but the further areas are from the central meridian, the more distorted their shapes will be. An interrupted sinusoidal map solves this distortion problem. If you could peel the rind off an orange in one piece and flatten it, the orange rind would have gaps, like an interrupted projection. Atlas maps of areas that are in the mid-latitudes are typically shown with conical projections. Notice that parallels are represented by arcs of circles, and meridians come closer together as their latitude increases. These maps are similar to what you see on globes, but they can only show small areas. Conical projections cannot be used for world maps. Google and other computer maps use cylindrical projections of the world that distort the relative sizes of areas. However, most people use Google Maps to view cities and state highways. Google City Maps are based on data from the U.S. Geological Survey. They make their city maps with transverse Mercator projections. In a standard Mercator projection, the cylinder contacts the Earth at the equator. In a transverse projection, the contact occurs at the central meridian of a city. This results in very little distortion for the small number of degrees of a typical city. Projections can also be constructed with purely mathematical relationships. This pseudo-cylindrical projection is not based on the relationship of the spherical Earth and a cylinder. All quadrangles simply contain 10 degrees of longitude and latitude and are perfectly square. The manual map projection is also constructed mathematically rather than geometrically. There are either 15, 10, or 7.5 degrees of latitude in a square. This approximates the preservation of direction and shape of a Mercator projection, although it's not as accurate. Its advantage is the ease of constructing its grid of square quadrangles and the ability to use existing grids of squares on which to make maps. Its format of 24 squares also provides a system for memorizing locational information. The app's 18th map is of the sky. It uses the same 24 squares, and each square has the same blue and red zone. Looking up from the Earth, everything in the sky appears to be moving. Clouds randomly drift around, but the movement of the sun and the stars repeats the same cycle every year. The moon and the planets move according to their own cycles. Every day the sun rises in the east, and when the sun sets in the west, you initially see whatever stars are to the east of it. These stars will also set in the west before the sun rises again in the east. On the sky map, the east and west directions are reversed. East is on the left side. The shaded areas indicate the Milky Way. All of the stars you can see without a telescope are in the Milky Way galaxy. It's a spiral galaxy that is shaped like a flat disk. There are no images of it, but there are images of hundreds of thousands of similarly shaped galaxies that can be seen with powerful telescopes. Our sun is in the thin middle layer of the galactic disk. Stars in the sky map's shaded areas are also in this thin disk, which is colored green in the diagram. Other stars are in the beige-colored thick disk. These stars surround our galaxy's center and its thin disk. There is also a galactic halo above and below the disks that contains clusters of a relatively small number of stars. Our sun is between the Perseus and Sagittarius arms of our galaxy. The Sagittarius arm is between us and the center of the galaxy. This is where the Perseus and Sagittarius constellations appear on the sky map. A cross mark indicates the galactic center to the right of Sagittarius. 180 degrees away is a cross mark to the lower left of Perseus. This is the point on the Perseus arm that is in the opposite direction of the center. There is also a cross mark for the North Galactic Pole near the center of the map, and one that indicates the South Galactic Pole 180 degrees away on the right side. One of the concepts that a star globe helps you visualize is the relationship of the Milky Way to the galactic poles. The North Galactic Pole is positioned at the top of the ball on the left, and the South Galactic Pole is at the top of the ball on the right. The Milky Way can be seen to run halfway between the poles. The grid on the sky map corresponds to the grid of latitude and longitude on the Earth, but it is projected out into space. The celestial equator is the Earth's equator projected out into space. The curved line is the ecliptic. It's the apparent path that the sun travels in the course of 1 year. The moon and the planets also move along the ecliptic. Instead of latitude and longitude, positions in the sky are given in units of declination and right ascension. Declination corresponds to latitude, and it is measured with the same north and south degrees. However, degrees of west and east longitude are measured with 24 hours of right ascension. Right ascension hours are numbered from 0 to 23, moving from right to left on the map. Hours are each divided into 60 minutes, and minutes are divided into 60 seconds. On the spring equinox, the sun crosses the celestial equator. The sun is indicated by a yellow disk on the map. The 5 visible planets are also displayed at their positions on the ecliptic. These positions are for the spring of 2023. Saturn and Jupiter are represented by blue and green disks. Mars is red, and Venus and Mercury are orange and brown. Every day, the sun moves about 2 minutes of right ascension to the left, which is about 1 hour per month. The moon moves about 49 minutes of right ascension every day. It travels the full length of the ecliptic every month. After 3 months, the sun will reach its highest position in the sky for people living in the northern hemisphere. This is the summer solstice. In places like Australia, it is winter time and the sun is in its lowest position. Notice that the app lets you replace the hours of right ascension with the months of the year. June is winter time down under. You can now see a crescent moon to the left of Mars. On the autumn equinox, the sun again crosses the celestial equator. Mercury and Venus have traveled along with the sun. All the planets usually move to the left, but the positions of Saturn and Jupiter have not changed very much. In fact, Saturn has actually moved slightly to the right. This is because all of the planets will at some time start moving in the opposite direction. This is called retrograde, and it's due to the relationship between the orbits of the Earth and the other planets around the sun. The sun reaches its furthest point south on the ecliptic on the winter solstice. In 2023, the moon is close to Jupiter and will be full in 7 days. Note, Mercury appears inside the sun's disk. It will actually be hidden behind it. All of the planets are shown larger than they actually appear. On rare occasions, Mercury and Venus do pass in front of the sun, but they are so tiny in size, in comparison, that you wouldn't notice it. Solstices and equinoxes occur because the axis around which the Earth rotates every 24 hours is not perpendicular to the plane of its orbit around the sun every 365 days. The sun moves 23.5 degrees above and below the celestial equator because the Earth's axis is tilted that angle to its orbit. The sun appears to move along the ecliptic because the Earth's orbit around the sun places it in front of 12 different constellations. These constellations are called the zodiac. However, they are not the same as the signs of the zodiac. The areas of the signs can be displayed above the map. You can see that the constellations for which they are named have all shifted about 2 hours or 30 degrees to the left over the last 2,000 years. This is called the precession of the equinoxes, and it's due to the wobbling of the direction of the Earth's axis every 25,920 years. The sun currently appears to be in the constellation Pisces during the spring equinox. 2,000 years ago, it was in Aries, and will eventually be in Aquarius. You may have heard of the Age of Aquarius. There is even a song about it you can listen to on YouTube. The plane of the moon's orbit around the Earth is nearly parallel to the ecliptic, but the slight difference is why lunar and solar eclipses are rare events. When a full moon occurs, it will always be 12 hours or 180 degrees from the sun on the sky map. Full moons always rise as the sun is setting. Quarter moons are 6 hours from the sun. A waxing quarter moon begins to rise at noon. A waning quarter moon will set at noon. Most of the planets orbit the sun in the same plane as the Earth's orbit. The sun spins around an axis that is perpendicular to most of the orbits. The closer a planet is to the sun, the shorter its orbit. Mercury completes its revolution around the sun in only 88 Earth days. The circumference of its orbit is shorter than other planets, but it's also traveling faster along its orbit. The sizes of the sun and the planets are not to scale with the size of the orbits in this image, but you can see that the orbit of Mars is larger than Earth's. It takes Mars almost 2 years to orbit the sun. When the Earth overtakes it, it causes the Mars retrograde, the apparent reverse in direction of its movement along the ecliptic. If we zoom out, we can see the orbits of Jupiter and Saturn. The blue planet in the distance is Uranus, which cannot be seen without a telescope. Jupiter takes almost 12 years to orbit the sun, and Saturn takes 29.5 years. Jupiter actually has 95 moons which orbit it. On a clear night, you can see its 4 largest moons with a pair of binoculars. If the following night is also clear, you can see that the position of the moons have changed. Galileo was the first person to see these moons orbiting Jupiter in the year 1610 using a homemade telescope. This was an important discovery that changed the way people viewed the world above us. The Greeks had accepted that the earth was a sphere since the time of Aristotle. Around 50 years later, Aristarchus proposed that the sun was the center of the universe and the earth revolved around it. 400 years later, Ptolemy compiled the observations of Greek geographers and astronomers into an atlas. Remember that Mercator would later use this atlas as the basis of his world map. Like most people at the time, Ptolemy believed that the earth was the center of the universe, and everything revolved around it. His atlas included detailed tables that accounted for the retrogrades of planets with loops within their orbits. In 1543, shortly before his death, Copernicus published a book which described a sun-centered model of the universe. Galileo's discovery seemed to confirm this model. A few years later, the astronomer Kepler published a much more detailed description of a sun-centered model. It contained the laws of planetary motion that we still use today. They provided the math and geometry for the size, shape, and velocity of the orbits of each of the visible planets. A little more than a century ago, astronomers proved that the sun was, like all the other visible stars, revolving around the center of a galaxy. The first galaxies outside the Milky Way were also then discovered. Considering that stars are revolving at both great and different speeds around the galaxy, you'd expect that the positions of the stars on the sky map would be changing. And actually they are, but very slowly. It takes more than 70 years for zodiac stars to move just 1 degree on the map. The distances of stars in the same constellations change in different ways and in their order of brightness. However, because the galaxy is so large and all its stars are moving around its center, the sky map changes slowly. The study options are different for the sky map than the 17 Earth maps. The hours of right ascension is selected by default in the sky map study mode. You can alternatively display the months of the year or the signs of the zodiac above the map. The Stars button displays icons for the 100 brightest stars. Pointing the mouse over these icons will display information about a star next to the map. The Constellations button displays the names next to each constellation on the map. Buttons with the numbers 1, 2, 3, and 4 appear on the next row, and the brightness button to the left is selected by default. Initially, the number buttons will each display 25 star icons by the magnitude of their brightness. Clicking the distance button will cause the number buttons to display icons according to their distance from us. This is the sky map with the icons displayed for all of the 100 brightest stars. The size of the icons are based on a star's magnitude of brightness. In the early 20th century, astronomers discovered they could categorize stars by their magnitude of brightness, not their apparent brightness, which is also determined by their distance from us, but their absolute magnitude of brightness. This is measured with an inverse logarithmic scale, but it can also be expressed with a simpler luminosity scale, in which our sun has a luminosity equal to 1. The brightest stars can have luminosities of 1 million, and the dimmest stars are less than 1,000th as luminous. When stars are also categorized by their temperatures, which correspond to the color of their light, a pattern emerges. Most stars are classified as main sequence, with each dot representing a star. You can see this forms a diagonal curve of very hot and luminous stars, starting in the top left and ends with cooler, less luminous stars at the bottom right. Above and to the right of the main sequence, you can see clusters of dots that are labeled as giants and supergiants. In the bottom left are the white dwarfs. Stars evolve over time. They begin when hydrogen molecules are attracted by gravity to form a sphere. The gravitational force then causes the hydrogen to form helium atoms deep in the core of the star. This fusion process is what generates light and energy. The amount of hydrogen a star begins with determines how it will evolve. Our sun is considered an average-sized star. It has been fusing hydrogen for about 5 billion years. Some of the helium has also fused into carbon and oxygen at the core. The sun is expected to continue this process for another 4 billion years. But as the denser core grows, the hydrogen fusion process shifts to a spherical shell outside the core, and that will cause the sun to expand into a red giant. Its core will eventually collapse into a white dwarf and will separate from the outer shell, which becomes a nebula of gas and dust that can potentially form a planet. The evolution of a massive star that contains more hydrogen happens more quickly. These very luminous, very hot stars not only fuse hydrogen into helium and lighter elements like carbon at a much faster rate, they also fuse heavier elements within their cores like iron, gold, and uranium. They expand into red supergiants as their hydrogen dwindles, and then explode into supernovas, which can either result in neutron stars or black holes. This diagram shows the additional classifications of giants and supergiants of stars as they transition from the main sequence. Note that average stars like our sun are considered dwarfs. The sun is categorized as a yellow dwarf. There are many red dwarfs in our galaxy, but they don't emit enough light to be visible to the naked eye. Below the red dwarfs, there are brown dwarfs, which don't fuse enough helium to emit any light. The planet Jupiter is a brown dwarf. Jupiter is one of the brightest objects in our sky, but what we see is reflected sunlight. This is how the 100 brightest stars are positioned on the Hertzsprung-Russell diagram. For example, this is the plot for Sirius, the brightest star in our sky. It is actually a binary star, a white dwarf revolving around a main sequence star. This is an example of the information that is displayed next to the sky map when you point at a star's icon. Clicking on a star icon will open a new tab with the star's Wikipedia article. The order of brightness of a star is given first, followed by its radius compared with the sun. Sirius's main sequence star has 1.7 times the sun's radius. Alpha Canis Majoris is the scientific name for Sirius, which is 9 light years away from us. Deneb is the 20th brightest star in the sky. It's classified as a white supergiant with a radius that is 203 times that of our sun. Alpha Cygni is 3,000 light years away, which is the furthest distance of any of the 100 brightest stars. Our galaxy is about 100,000 light years wide, so the stars we can see without a telescope are in the same area as we are in the galaxy. There are roughly 100 billion stars in our Milky Way galaxy. The names of stars and constellations are not easy to remember because they are primarily Greek, Latin, and Arabic. For example, Deneb is Arabic for tail. The constellation Cygnus is Latin for swan. Shortly before telescopes were invented in the 1600s, Johann Bayer created a system of naming stars that eliminated the Arabic names. He used the sequence of Greek letters like alpha, beta, gamma to designate stars in a constellation by their brightness. Deneb became Alpha Cygni. Cygnus is a Latin noun and Cygni is the Latin adjective. Without a telescope, Bayer couldn't always identify the correct order of brightness. He relied on Ptolemy's magnitude classifications and simply listed the northernmost star first if more than one star in a constellation had the same magnitude. Ptolemy did not include stars in the southern hemisphere because Europeans had never seen them before they sailed south of the equator. Bayer devised his system mainly to give names to stars like Alpha Centauri, which doesn't have any other name. Some southern constellations were given English names in honor of the newest inventions of their day, like clock and telescope. On the sky map, many of the Latin names of constellations have been translated into English. The sky map quizzes will help you to learn the names of stars. They group stars by their magnitudes of brightness in 4 separate quizzes. Sketching and labeling stars and constellations is also an effective activity for learning their names. However, there are some differences from how the Earth maps are sketched. The buttons provide you with the same tools, but there are no west and east buttons for copying left and right sides of the map. Instead, there are 4 number buttons. These let you check whether you have correctly copied stars according to their magnitude of brightness. You can see that the default dot size is 4, which is best for bright stars, but should be decreased for dimmer stars. Constellations, unlike coastlines, are not actually real. Other civilizations like the Chinese and the Mayans grouped stars in completely different constellations. When you sketch the sky map, you start by using the dot tool to locate stars. Use blue or red dots to make associations for remembering their locations inside the 24 primary squares. Magnitude 1 stars should be located first. Clicking the number 1 button will dim the constellations and display these stars' icons, which your dots should overlap. Note any stars you missed, and then click the dot button to continue. Use the size field to reduce the size of dimmer stars to approximate the same sizes of the icons. Size 4 works for magnitude 1, size 3 for magnitude 2, and size 2 for both magnitudes 3 and 4. Size 1 is too small for individual stars, but it's the best choice for Orion's belt. These 3 stars are actually magnitudes 2 and 3. Size 1 dots result in the most accurate spacing between these stars. The belt makes Orion one of the most recognizable constellations in the sky. Stargazers often check out the magnitude 1 star above it. Its name is Betelgeuse, and it's the next red supergiant that is expected to explode into a supernova. Sketching constellations is best done by tracing them with the line tool set to black and a size of 1. The style of constellations used on the sky map were developed by H.A. Rey in 1952. Several of them have replaced the former designs. Compare the traditional style of Gemini with the more descriptive design by Rey. Rey is better known for his series of children's books based on a monkey named Curious George. However, his book, The Stars, is recognized as an excellent introduction to astronomy. Click the grid button to view your sketch of the sky map. You needn't draw all the constellations, especially ones without any bright stars. You can just label those. Using black for constellations and blue and red labels for stars is the clearest way to label them. The best activity for complementing your study of the stars is making a star globe. The materials and steps for making a star globe are similar to an Earth globe. After you make the crayon grid, you add the ecliptic with 2 contrasting colors. I used yellow and red. My yellow segments of the ecliptic correspond to even-numbered months. You then add the Milky Way before sketching the constellations. Remember that constellations are formed by connecting stars with straight lines. But on your ball, you first locate the stars with the same marker that you use for the lines. Then you use a white marker to indicate the brightness of stars. You can erase the grid before or after completing the stars. If you compare a star globe with an online star chart, you will see that your basketball has become a guide to the night sky. The stars that will be visible after sunset are to the left of the position of the sun on the ecliptic. The stars that will be visible before sunrise are to the right of the position of the sun. This is a view from the northern latitudes after sunset in mid-May or an early morning in November. The yellow and red ecliptic segments below Leo show the position of the sun in August and September. There are links to a couple of online star charts in the gallery section. They attempt to identify your latitude and time zone based on your IP address. Tilt the top of the ball toward or away from you to adjust the view to your latitude. You can see the Big Dipper constellation in the top left of the online star chart and on the top left of the ball. When you compare the relative positions of the stars of Leo and Gemini, it's apparent that the star chart shows more of the sky than the ball does. In this view of the ball, we see the Great Square and the 3 bright stars of the Summer Triangle to its right. Deneb is the bright star to the right of the ball's curved stripe. When we compare these stars with the chart, we see that less sky is again visible on the ball. This can be explained by comparing a planar projection with an overhead view of a globe. You can't see areas immediately above the equator on a globe because they are turned almost 90 degrees away from your line of sight. However, star charts are based on looking at the sky while facing different directions. This planar projection of the Earth is based on a center contact point at 90 degrees north. The contact points of star chart projections are based on your latitude and longitude. The chart and star globe are both models of the celestial sphere. However, we are inside that sphere at the center, so it's possible to see a full 180-degree view of it. Stargazers also know that when you attempt to view stars on the horizon, the amount of atmosphere we look through usually blocks the light. The celestial sphere is just a geometric concept for calculating the declination and right ascension of stars and planets. The sky map doesn't have a scale. The distances between stars on the map are unrelated to the actual distances between them in our Milky Way galaxy. The term double star refers to two stars that are nearly aligned from our point of view, but can actually be hundreds of light years apart. We are closer to some of the stars in the Swan constellation than Deneb is. The sky globe is an example of a convex-concave illusion. This hollow face illusion is another example. These two faces are views of the front and back of the same plastic mask. The sky globe is a useful illusion. If we could view the stars from outside the celestial sphere, they would be flipped vertically to how they appear from the Earth. For example, the Great Square would actually be to the right of the Summer Triangle. However, that star globe would not be as useful for identifying stars and constellations in the sky. There are other types of objects in the galaxy besides stars, including planets. Planets outside our solar system are called exoplanets. Identifying planets that are similar to ours is a primary goal for many astronomers. They now have space telescopes above the Earth's atmosphere, which are capable of identifying them. The good news is that there are billions of planets in our galaxy. However, a planet that offers the kind of environment we need has not been found yet. The more you learn about the universe, the more precious the Earth appears to be. The benefits of Earth and Sky Camp activities are obvious for the study of geography and astronomy. They can also prepare students to better understand advanced subjects like geology, ecology, and economics. Astronomy will complement core subjects like physics and chemistry, just as geography complements the study of history. The manual map puts the world in your hands. When you can accurately communicate with others about the world, you can work together to make it a better place. Check out manualmemory.net to get started with Earth and Sky Camp, as well as other visual learning applications.